All those one-year-olds tweeting about advanced geochemical analyses.
You're listening to the Cosmic Cast.
Hello everyone, welcome to another episode of the Cosmic Cast. The reason I'm speaking in this hushed, quiet tone to you all is because we're in a terrible room to record this podcast, and you can probably hear me echoing even though I'm talking very quietly. Today you're with me, the disenchanted diplomat, Rick Viver here. To my left, we have the arithmetic aviator, Marissa Lowe.
Hello.
In front of me, we have the juvenile geranium, Dr. John Pennant Fisher.
Hello there.
And today we have a guest. He was born in a bayou, Tom Harvey.
Hello, how are you doing?
He's not really a guest, he's regular co-host, Tom Harvey.
Today, he is the one we are interviewing.
The spotlight is on you today, Tom.
We've realised that we've not really talked about your project at all in any great depth.
No,
so
I've flown under the radar for a whole year.
So your time has come.
My time has come.
Plot twist, you're actually not even a student here. You're not even part of the research group. You've just been here.
I'm just really friendly. I just turn up at the right times every week.
Well, you were just here when we ordered the recording equipment. And
just by chance, yeah. No, that is exactly what happened.
Exactly, yeah. So what actually brought you to study, to do your PhD at the University of Manchester?
When I was at school, I really liked doing... I did the IB, so I was kind of...
International baccalaureate for all those
Because you were in America.
Because, yes, my family
was
was
born in a bayou.
As you can tell from Tom's accent.
As you can tell from my accent.
Texas accent.
Yes.
Born in a bayou.
So was that an international school?
It's a British curriculum international school, yeah. And I was privileged to be able to do maths, physics and chemistry in addition to kind of other subjects. And what I was really looking for when I kind of applied to university was the ability to keep doing as much of that as possible. And so I did a geology undergraduate, which kind of fulfilled that really well, because I got to do maths, physics, chemistry, biology, and in some ways a bit of history as well, which was really neat as a kind of nice interdisciplinary subject. We did a very classical kind of undergraduate degree, lots of looking at rocks, not very much using computers. And I think I've probably done quite well for that because, well, it's actually been great recently. I've been demonstrating and stuff, and it's quite cool to go back and revisit some of that. But in my third year, we had the option to do a planetary science course, and actually there we were taught, all of the kind of basic planetary geology things about the different planets, about the moon, and we were taught about the lost meteorites of Antarctica. So when I was applying for which is this, these buried iron meteorites that Katie Joy has talked to us about before. And so when I applied, I saw that there was a project associated with that at the University of Manchester. And
so you came to the UK, didn't you, to do your undergraduate?
Yes, sorry, no. So I did my undergraduate at Royal Holloway, and then I did a master's in geoscience at UCL, and
was it a large culture shock going from the bayou to UCL?
Not really. I mean, we'd kind of moved around a bit, so I was kind of quite flexible with how I was prepared to fit in and everything. And I've been at a British school and everything, so it was not a massive shock. Yeah.
Was there ever an option to do your degree in America?
It would maybe have been an option. I wasn't massively
really expensive,
isn't it? It's very expensive. I guess, and my family are all here, so aside from my immediate family,
would you have paid fees?
Yeah. Unless you get a scholarship or something, I think. But so the whole way through my degrees, I kind of veered more and more towards a petrology and geochemistry theme with my subjects. And
did you have to do like a project for your BSc, or did you do masters as well?
Yeah, no. Well, so I did a kind of mapping project for my undergraduate. We mapped in Loch Erebol in Scotland, which was lots of deformed mylanites. It's kind of the expression of the Moyne thrust almost, which was fantastic. And then for my master's project, I looked at terrestrial metals, iron nickel metals called Josephinites, which crop up in the Josephine ophiolite in Oregon and Northern California. And so that was kind of my in on metals.
Am I right in thinking ophiolite is an area where the thingy crust, the oceanic crust has been pushed up to the surface?
Yeah. And that was a really fun project. It was really interesting to get into kind of some of the looking at preliminary metals and things. which we'll talk about in a bit. And after that, the opportunity to carry on doing the same sort of analyses, but looking at solar system materials was just quite a big draw. And it's been a bit of a steep learning curve because, of course, there's massive volumes of literature on any subject. So it would be a steep learning curve to start any PhD. But it's been really interesting.
Was Manchester your only choice? Did you just go?
No, I applied a couple of other places as well. They were kind of all metals projects, though. There was a project at Leeds looking at pallasites. And we actually know the person who's doing that project, and she's probably doing it much better than I am. So, and then I also applied
Shout out to Maeve.
Shout out to Maeve. And then I also applied for a project at Cambridge, but that was a paleomagnetism project.
Oh, so very different. Yeah.
So it would have been quite different.
Yeah.
Probably much more mathsy. So I'm actually a little bit relieved that it's turned out the way that it has.
Did you feel welcomed when you came to Manchester University?
Yeah, well, I mean, they put me next to this really strange guy in the office.
I've heard he's very handsome.
I think I was in the same one.
Yeah,
I don't know.
I mean, aside from that, though, it's been grand, yeah.
Would you describe him as
except for him specifically.
Would you describe him as a disenchanted diplomat?
I probably would, yeah.
Yeah, there we go.
Yeah.
I think I know him. He's very attractive.
They were in the same office.
Yeah, that was, for the
Thank
listeners.
you, John.
We were in the same office, yeah. So for the listeners, you are now in your second year of your PhD.
I am in the second year of my PhD. My project looks at metal in meteorites, really. It's a bit broad because, well, it's not just even meteorites. I'm hopefully going to be looking at some metal in some lunar samples as well. Specifically
metal across the solar system.
Yeah, why focus on one thing when you could, have the luxury of looking at a few? I think when most people think about metal in the context of meteorites, they probably think about iron meteorites, which is fair enough because they are, entirely made of metal. But metal is a very common component of solar system materials, not so common on Earth because of how much oxygen there is, so everything always is in its oxidized form. But these kind of metals, like you might see metal in a piece of steel or something, is an important fragment, is an important component of lunar materials, chondritic materials, all sorts. And it actually records quite important information about the bodies that material comes from and the processes that body has undergone, whether that's kind of planetary evolution or whether it's processes like impacting and impact melting. And impact melts are the focus of my project. So we use the composition of the metal that is in those impact melts to try and understand the materials that went into an impact.
So just for the listener, do you want to define what an impact melt is?
Yeah, so when two objects collide in space, there's a large transition in energy from the kinetic energy of the bodies that are colliding. That's converted to heat, and that is able to melt and in some cases even vaporize quite a large portion of both what we call the target and the impactor, although sometimes both of them are impactors, materials. And what that results in is complete melting of a very heterogeneous body, potentially, and all of that is whipped up into this melt. And in impact melts, and when those impact melts crystallize into a rock, when they cool down, we see a really interesting range of kind of lithologies and textures, with some really strange minerals in them as well that are kind of a product of that impact process.
And the reducing environment as well.
And the reducing environment in which these things are forming, because they're often forming in space where there's obviously no atmosphere or anything like that. And so if you imagine that process is basically sort of mixing of two materials, we look at the metal particles in these impact melts that we see to try to kind of unpick that process and gain a better understanding of the two materials that went into that impact that formed the impact melt.
How does an impact melt get to Earth?
So when the impact happens, in kind of easily visualizable settings. You have an impact crater, which is kind of easy to visualize, and some component of the lithology associated with that impact crater will be impact melt. And then there'll be other impact lithologies sometimes called impactites, associated with it, like swavite, which is a sort of impact breccia, or like fault breccias and fault glasses. And then later impacts into that same surface can eject material. I mean, some material can be presumably ejected by the initial impact that causes melting, but lots of these things are kind of polyphase processes because these surfaces are constantly being impacted into. So, and then, once that material has been ejected, it can come to Earth as a meteorite.
Okay, so say there's an impact between the impactor and, say, an asteroid to begin with, and that creates a crater on the asteroid. What sort of scale of impact melt is formed from that? I'm sure it varies, but, will it be across the crater? Will it just be like small areas? How much will there be?
It depends on the size of the impact. If the impact's large enough, you can have a colossal melt pool of impact melt in the center of a crater, and then if it's a smaller impact, sometimes you get like dikes of injected impact melt in some areas, and some kind of heterogeneous impact melt pooling. So it really does depend on it depends on a whole host of properties associated with the impact, the lithology of what the material's made of, both for the impactor and the target, the angle of impact, because that controls how deep of an impact crater you might get, and then the shape of the impact crater actually has implications for the way that the impact melt then kind of moves inside it. So there's a whole kind of range of reasons why you might have more like one or more like the other.
I guess the point is you look at these actual impact melters to figure out what the formation process was.
Yes. So most of my work so far has been looking at these fascinating CB chondrites, which are carbonaceous chondrites named after the type specimen Ben Cubbin, and they have loads of metal in them. Typically, it's common in impact melts to find between sort of 1 and maybe 10% metal, but these can actually range from 60 to 80 volume percent metal, which is a colossal amount. And what's really interesting is that the metal in these samples are thought to have formed in an impact melt vapor plume on the CB parent body. So that is interesting because it's tied to the impact melt story in that way. But further, more impacts over time have happened on the CB parent body where this material was sitting, having formed, and more impact melt has been injected around some of these metal particles. And what that means is that it sort of behaves as a microcosm for the impact melting process, because we can kind of really focus on how the impact melt has affected the metal in those textures, and try to understand, when we want to understand things about composition of the parent body of some of these impactors, what processes have affected the composition of that metal after it was formed. Because if we want to make good conclusions based on those compositions, then we want to make sure that the compositions of that metal actually reflects the composition of the parent body to some extent. And so that's been really interesting.
Do you often get material left over from an impactor as opposed to the body being impacted?
It does happen.
Yeah.
There are proposed relic grains, I think, especially in some lunar impact melts.
It's quite rare, though, isn't it?
It is quite rare. It's quite common, especially on the moon, for the impactor to be largely melted or vaporized as part of the energy of the impact.
Because if you're melting rocks on the moon, say, you're going to be at a temperature where you're going to melt the impactor anyway, I think.
Yeah.
Yes. But within, I think, some regolith samples, there are proposed fragments of meteorites that might have kind of been spalled off as they entered.
You actually see this more thinking about it in Western samples, like howardites and things. You quite often get carbonaceous chondrite clasts within eucharites. Was it eucharites? Howardites are the breccias, eucharites are the...
Is that because of a reduced impact speed? Or?
I'm not really sure why they get preserved, but I just know that you do see them more often in those sorts of samples.
Well, I
than you
mean,
do
I
for
think
the
they've
moon.
actually proposed that there might be terrestrial material on the moon.
Oh yes, there was
Yeah,
that
yeah.
paper that reported that zircon, wasn't there?
Yeah, that
was
some of the
supposedly from
material
Earth.
is actually blasted off in that direction can survive.
Yeah.
So it is possible, and I'm hoping we've applied for some samples, and I've included in that application some potential, I think, relic meteorite fragments, and I'd be fascinated to have a look at their composition and see how their composition might have changed as a result of that impacting process.
I mean, I guess like the moon in a way is the ultimate impact melt. If you think about it, because I guess that was an impactor impacting the Earth, and it was so large enough that you had a whole igneous differentiation sequence occur.
This is for people who don't know. It's thought that the moon originated from Earth when a large impactor called Theia, which is around the size of Mars. They believe, hit the proto-Earth. And blew off a load of material into space, and that coalesced to make the moon.
Although it's actually quite fascinating. We Marissa and I, we were reading a paper for one of our kind of tutorial groups the other day about this concept called the lunar synestia, which was very complicated, and we won't go into too much detail on it. But I mean, they were basically discussing the formation of the Earth-Moon system in a kind of impact melt vapor donut.
Torus, if you will.
Yeah.
Oh, what?
I think donut sounds much more approachable.
But the proper name is...
sort of a cloud of debris in a donut shape around proto-Earth.
Yeah.
Was sort of the thing they were envisaging.
Yeah.
I assume this is from modelling.
Yeah.
Yeah.
But so these are immensely complicated systems, and that's why it's really neat to look at the really kind of fine scale compositional changes and textural changes. So part of what I've been looking at is the composition of these metal particles and how the composition of those metal particles kind of varies with how much they've interacted with the impact melt. And I'm also using a technique called electron backscatter diffraction, which allows you to understand the crystallographic microstructure of these metal particles, to look at how they've, essentially been annealed or not annealed by the heating of these processes. And lots of this has actually required
So what
reading.
does annealed mean?
So annealing is the kind of crystal growth associated with reheating that you might have heard of in the concept of blacksmithing or something. And that's kind of an interesting tie-in, because lots of the papers that I've been reading have actually been material studies papers. So this is a technique that's widely used in the study of construction steels and things like that for hardness and understanding how they respond to strain and stress and heating and all of that kind of thing.
Because I guess the metal you're looking at are alloys. It's not just pure iron, is it?
Yes, exactly. So all of these kind of mild steel papers have been quite useful in trying to understand how this impact melt has heated the metal and how that's had an impact on the metal's microstructure.
Because some of the elements you get in this iron are things like nickel.
Yeah,
cobalt,
predominantly nickel, cobalt, phosphorus, chromium.
So those alloys are actually being formed
naturally,
due to the impacting that's occurring.
And in fact,
those elements are kind of naturally alloyed with that metal, even before impacting in some instances.
Yeah, but the high nickel content is unique to meteoritic metals. So if you were to have an extreme reducing environment on Earth and you were to crystallize out iron from a magma, you wouldn't have anywhere near as
much nickel.
Nickel,
that's right.
Yeah.
And there are
Is that a result of differentiation process that forms a planet, or
it's to do so all of these compositions are to do with the pressure, temperature and kind of oxygen fugacity, which is basically how much oxygen is available to react, conditions of the system. And
so that's what we're talking about when we're talking about reducing environments as well.
Exactly.
Yeah, exactly.
And there are some terrestrial ions.
Very rare, though.
Very rare, like the Disco Island ions.
Yeah.
Disco Island,
yeah.
Damn it, Tom, why aren't you doing those? They sound great.
No, they are. They're really, really interesting. Some actually quite large pieces of metal as well.
Yeah, like person-sized boulders have been found
Where
on the
is
beaches.
Disco Island,
It's in
dare I
Greenland.
ask?
Greenland, yeah. I think we could wangle a field trip, maybe.
Probably, yeah.
Yeah.
Well,
I'm sure that would be fascinating, actually. And
So they found samples there that have similar nickel-iron content?
No. So they are terrestrially forming ions, nothing to do with impacts.
It's where magmas...
So they have a very different composition. They don't have the nickel in them.
Magmas are interacting with carbon-rich lithologies like coal seams, and it's effectively turning the magma chamber into a blast furnace, precipitating out, causing the reducing conditions needed to precipitate out iron.
But it's interesting because impact melts on Earth, like the Sudbury Igneous Complex, are much more sulfide rich than they are metal rich, and that's again as a result of the kind of oxidizing conditions. But yeah, so the really interesting thing about the microstructure is that it allows us to try and investigate the thermal history of these particles, what processes were actually occurring on the parent body that were affecting them, and potentially also some strain history as well. So that's kind of all in process at the moment, but I've kind of recently made some good progress with that, and I'm really excited to see where those data sets kind of take us with some conclusions.
I guess we've just covered all the bits that you can learn from these meteorites. What samples are you looking at in particular?
So far I've focused on these CB chondrites, these fragments of a meteorite called Gujba, which is famous because its metal particles are a real range of morphologies. So some of them are seemingly pristine, they're very well rounded, they're spherical in some instances, and they get up to being...
You see yourself in those particles,
yeah,
pristine, well rounded.
See my beautiful face in that mirror sheen. And they get up to be sort of centimeter scale in size, but it's also famous for having, a significant amount of impact melt material between these metal particles, kind of mechanically and chemically deforming that metal. And so what I said earlier is a microcosm is because you have the kind of a real range of metal silicate interaction textures, which means we can look at kind of what does a pristine particle look like, what does a really deformed particle look like, and then the goal is, with that information in mind, look at a broader sample suite of lunar samples, for instance, which have less metal in each one, and with that kind of understanding developed from this kind of type specimen almost for metal silicate impact melt interaction, try and understand more about the processes that have affected that lunar metal.
Okay,
and so those are the samples that I've applied for.
So the different things that you've learned from the different textures in Gujba, you can sort of apply that to other samples from the moon and other places. Okay.
Yeah.
So once you return, someone gives you a sample, say for instance you get a lunar sample, what do you plan to actually do with the sample itself?
So the state of the sample that you get kind of dictates that in a certain... If someone just gave you a meteorite and it was not prepared in any way, you'd have to figure out how to section it, you'd have to polish it, all of this sort of thing. I'm quite fortunate in that most of the samples, well, all of the samples that I've looked at or wanted to look at have been pretty much prepared already. So these samples of Gujba are ones that my supervisor, Rianne, had worked on before. And these lunar samples that you apply for from NASA come prepared thin sections,
right, okay.
which I think it makes a lot of sense because the best way to make sure that none of that material is wasted is to make sure that it's very carefully distributed and that sort of thing. Because if everyone just got a piece of moon rock and chopped it up, then we'd lose a lot of it, and that would be a great shame.
Because you only need small amounts of each rock, but there's such a limited amount. Exactly.
Yeah. And
so these thin sections are sections through the center of a meteorite, or
through a center, through
area,
it depends, depending on how kind of homogeneous your sample is. You could either take a section through the middle and it would probably be pretty representative, or you could take a section through something that's interesting if there's only a little bit of it. So I kind of, prior to applying for these lunar samples, I went through looking at the lunar sample compendium, looking for information to make sure that the samples that we've applied for are ones that are known to have metal in them or known to have weird textures or, like potential meteorite fragments, something like that, so that we know we should have something interesting to work with. And then it's a case of just doing all the analysis on a kind of range of different analytical machines. We're using the scanning electron microscope, we're using the electron microprobe, which are just different ways of visualizing sample kind of compositions, whether more qualitatively, more quantitatively, all with the trade-off of time and analysis cost, depending on what it is that you want to know.
So where are you at then with all these analyses?
So I've done quite a bit of analysis. I've spent most of my kind of first year looking at Gujba. I've done quite a few probe analyses. I'm in the process of organising to get most of the EBSD data done, because I've kind of done a sample subset of one of the particles to kind of verify to ourselves that it was something worth pursuing, that there were interesting answers to be had from it. And I'm now trying to tie all of that together, and then hopefully, in a couple of months, whenever lunar samples get allocated, we will begin to basically go through the same process again, just on a wider sample suite. But in addition to all of this metals work that I've been doing, I initially applied for this PhD under the title, which is the Antarctic Meteorites Project, and as part of that, I have been developing a method for producing 3D models of some of the samples that are being brought back from Antarctica as a kind of joint curatorial and science motivated project. And so this technique is called photogrammetry, and basically it uses the concept that if you take a picture of something from two different directions and then use specialist software. The specialist software I'm using is called Agisoft Metashape.
Not a sponsor.
Not a sponsor. Although if they did want to, I'd love a sticker or something. And it can match pixels of kind of specific color. So it's really important to have your camera set up really well done. Match pixels of specific color, and then do that for an entire suite of images to develop a kind of visualization of the object, in this case a meteorite, in 3D space. And it makes these kind of, they're called point clouds, and you get increasingly complicated point clouds as it looks at the 300 or 400 photos and compiles them to form this 3D shape, which then becomes, a kind of object file, which we can layer a texture over, and then that means we can use an iPad or a computer or what are they called, the VR goggles or something, to view
that's what
that.
they call them, VR goggles.
VR goggles, yeah.
That's the company.
No sponsor. Yeah. to visualize that data, which is great from a kind of curatorial point, because you can see the sample maybe much bigger than you would be able to.
We're talking about very high resolution images.
Very, it's a 45 megapixel camera we're using, so it's millions of pixels. Yeah. I do need to show off a little bit.
But also it was with the aim of, once you start cutting open your Antarctic meteorites and analysing them, you have got a 3D record of them, basically.
Absolutely. So it's kind of heritage data that we wouldn't be able to reproduce once the samples have been split up. So it's really useful in kind of that context. I kind of have a vision that it would be useful for outreach and teaching, because of course this means we can show people really nice reproductions of the samples that otherwise have to be kept quite safely.
So I guess you can 3D print them.
Yeah. Theoretically, that's something that I'm hoping to do at some point. I know that somewhere in the university there is a 3D printing suite, and I'm going to find them.
Or even if you just transfer like the models on the internet in some way.
Yeah.
It's much more accessible. It's pretty good way to do outreach, I guess.
Well, exactly, and this is actually something that museums have been doing quite a lot of to digitize their collections, but this is the first time that I've kind of seen it done in this sort of meteorite context, and there's a couple of science questions as well that I'm hoping to address using it, which is pretty fun. It's a lot of time standing there, because it's all manual, so you take a photo, rotate the stage, take a photo, rotate the stage, take a photo, rotate the stage. But when you see the final product, which is a 3D model of a meteorite whizzing around on your computer, it's totally worth it. So that's quite fun.
And it's also quite cool because you're one of the first people who gets to look at one of the meteorites, at some of the meteorites that have been collected from Antarctica.
Yeah, absolutely. I always think it's very easy to get blasé about the materials that we get to look at, because they're so rare. And I mean, albeit we may not be looking at very much of them, but the fact that we get to spend time zapping space rocks with X-rays and electrons is particularly neat.
This is going to come as a massive surprise to you, but we ask all of our guests this secret question at the end of the talk.
I hadn't even noticed.
Wow, oh, okay, all right. Just having a nap in the corner for the final 5 minutes every time. So, Tom, if you could be doing something else other than looking at metals and meteorites in academia or outside of it, what would you want to do?
I think that doing probably a lot of similar techniques to the ones that I'm using, but to look at archaeological artifacts would be really interesting. So looking at the chemistry of tools.
Mummy toes.
Yeah, looking at the chemistry of mummy toes and tools and things that can be recovered kind of associated with a historical record would be really interesting.
Yeah, I kind of like those random things that you get where they're like, oh, we carbon dated this random old bowl to determine what people used to eat thousands of years ago or something.
Yeah, that is incredible.
There was actually a really fascinating thing in the news the other day about the fact that this team had I think they'd CAT scanned a mummy and used, basically they'd been able to reproduce the shape of its vocal cords. So they'd actually been able to reproduce the noise, a sound like the voice of a mummy. And I sort of was, I listened to it expecting something a bit spooky, a bit sort of Indiana Jones.
Sure, it just sounds kind of like a human.
No, the sound that they managed to recreate, which I'm sure loads of work has gone into, and it's really cool, but it's just kind of like, So
sorry, what does it sound like?
And so I was
Are you sure they had
a
mummy scanned a cat?
It was, but like as a kind of scientific effort, that's awesome.
That's the pinnacle of someone's scientific career, Tom.
Yeah,
CAT scanning
and
vocal
you
cords.
wish it was yours.
But yeah, so probably something relating to history, but still trying to get as
recent
much
history.
chemistry and analysis in there as possible.
Well, it's been a pleasure, Tom. Please never come back on here again.
Gladly.
And thank you everyone for listening to the Cosmic Cast. I should probably mention we are recording this on the birthday of the Cosmic Cast.
Yes.
Woo!
So if you don't like, comment, share, and subscribe,
All four, not just one of those. Then
what are you even here for?
Yeah.
That'll be our birthday present. It'd be...
Also, as our birthday present, you should follow us on Twitter. I don't think we've really mentioned that in a podcast before.
Yeah.
And the Twitter account is fine, by the way, guys. I may have accidentally gotten the account locked earlier this week because I thought, our birthday is coming up soon, and that Twitter notification always asking add your birth date to your account always keeps coming up. So I was like, well, it's our birthday, so I know when the birthday is. And I put something 2019, and it's all fine and dandy until I go on the account later and it says, you violated our age policy. Your account has been locked. And I was just...
How old do you have to be on Twitter?
13. But
I thought we were 1 year.
All those 1-year-olds tweeting about advanced geochemical analyses.
Yeah, so
Gotta hand it to
Twitter,
them.
kudos to Twitter. Your security is, watertight. The fact that you don't let 1-year-olds talk about planetary science.
And in kudos to because they resolved the issue within like an hour and a half as well.
Yeah.
But Twitter's not a sponsor, by the way.
Not sponsored, no.
I always assume the listeners will assume anything we talk about is sponsored.
Yeah, but we are at Cosmic_Cast.
And at Earth and Solar System.
Yes.
We will link both in the description.
Questions, comments. If you don't want to leave them on the YouTube channel, then send them to us on Twitter, and we'll do our best to get back to you.
Indeed.
And
to look forward to in the future, I don't know when this episode will be coming out, but we are planning to do a great series of videos as well in the future. So look forward to those. And thank you very much again for listening. I don't know if Tom had anything else to say, but I'm cutting him off.
Thanks, Tom.
thank you all very much.
Bye.
Bye.